Welcome to the Tech Ed Podcast, where we visit with leaders who are shaping, innovating, and disrupting technical education. People who are not afraid to think differently, not afraid to try something new, all with the goal of securing the American dream for the next generation of STEM and workforce talent. Welcome into the Tech Ed Podcast. Today we are asking the question, what happens when you are the director of a research center that receives a grant that may be the largest grant of its kind that your university has received in the last decade? We are going to talk all about that today with Glenn Daehn. Glenn is the director of the Hammer Engineering Research Center at The Ohio State University. Glenn, thanks for coming on to the Tech Ed Podcast.
Thank you so much for having me, Matt. Really appreciate the invitation and great to be here.
It's great to have you. And we're going to talk about the Hammer Engineering Research Center. So let's start out with that. It's spelled just like it sounds, Hammer. What does Hammer stand for, and what is the purpose of the center?
Okay. Hey, Hammer, we did a little acronym engineering here. It's hybrid autonomous manufacturing, moving from evolution to revolution. That's what Hammer is.
That's a mouthful.
And it's a mouthful, but it's a good acronym. Hammer is and one of the key processes that we have in this is actually kind of hammering using deformation. We feel like deformation has been underused as a process.
Okay.
So deformation has been a primary way we make shapes forever. It's also a primary way we improve the microstructure and properties of metals as well. So blacksmiths and so forth have used hammers forever. Drop hammer forging, all of this is part of it. So that's something that we want to include. That's one of the key processes in our hybrid autonomous manufacturing spectrum.
I know we're going to get into that in a little bit more detail as the discussion goes on, Glenn, but let's start with this. I understand you've got 70 partner organizations that are involved in this project. Tell us a little bit about your partners.
They include large companies, aircraft companies, forging companies, small startups. There's actually a lot of very interesting startups in this space of what we call autonomous manufacturing. Small companies, other educational institutions, full universities, community colleges, and very importantly, I think a little atypical for organizations like ours are the technical societies. We also we welcome in, and they're a big part of what we will do because we want to form standards and also join with them. They play really important roles in workforce development, bringing the community together, and they are a nice, non-biased, honest broker for lots of technology. So we want to really work with the technical societies, ASM, TMS, American Welding Society, Society of Manufacturing Engineers, ASTM, all of them. They're important parts of all of this.
Absolutely. Following 25 years in manufacturing, those are all acronyms with which I am intimately familiar. So credit to you and your team for including the technical societies. Absolutely. Also the small and mid-sized businesses. I think a lot of people may be a little less familiar with the world of manufacturing. Think about the huge manufacturing companies, the big three at the time. Automakers no longer big three, but large automaking companies, companies like Intel, Apple, Tesla, and they're obviously an important component of the manufacturing economy, a very important one. But equally, if not more important, is this whole sea of small to mid-sized businesses that are supplying directly to those large companies, or maybe supplying somebody who's supplying the large companies, and so on. And so it sounds like you've built out a pretty impressive group of these companies and organizations that are supporting your work. Any logic that went into kind of who you chased or who you put on the list as a likely target?
So I think two things we want to do is we want innovation. We also want scale. So we have a mix of innovators, and then we have companies that can help scale us out with these kinds of things. And we've got 4 other great partner institutions with that: Northwestern University, Case Western University, North Carolina, A&T, and University of Tennessee at Knoxville, and along with them, they have a great alliance with the manufacturing demonstration facility at Oak Ridge National Lab and all that. They're all part of our team on that.
This whole idea of hybrid autonomous manufacturing, that may be a term that's new to some of our listeners. Tell us a little bit about what that is.
So hybrid means use all kinds of processes. So, if you kind of look back at the history of manufacturing, CNC machining was a breakthrough. So that's a subtractive manufacturing process. Then we went on to use basically the same kind of G code to do additive manufacturing, to do deposition. And that's an addition process. The other big way that we make shapes is by deformation, and it's actually one of the most efficient ways of making shapes. If we forgings and sheet metal forming and all these things are deformation processes. Making cans, the deformation process. We change the shape, and while we do that, we also change the microstructure of the material. Right now, we don't have good numerically controlled methods for deformation. That's something that we really are going to lean into hard with this center is numerically controlled deformation. Once you have that, you can make the shapes, and then we can also do something like take a casting that may not be optimal, that may have some porosity and reshape it where we need it to improve the microstructure, improve the shape. And by mashing up these processes, we think we can do completely new kinds of things and do things that are more efficient than additive manufacturing in many cases. So right now, if you think about metallic additive manufacturing, you're usually thinking about a powder bed process. And again, it's a wonderful process. You get shape out of that, but it requires more energy than casting or deformation because you've typically got to make a powder. You end up melting that with a laser. You've got a lot of excess powder. All of that, if you can go direct by taking the shape and making it by numerically controlled deformation, you can get properties and you can get shape all at once. And that's basically what we're trying to do is develop numerically controlled deformation. And so that hybridization means taking things like addition, subtraction, joining, hybridizing them. The autonomous word in that means that we ultimately want to take the human, make the human a designer of this, not necessarily an operator of all of this. So you could actually transfer a part from, say, an additive manufacturing process, a wire arc additive manufacturing, to numerically controlled deformation, to machining tight tolerance surfaces, and do that in an autonomous way where the human doesn't have to be in the loop at every step. And also you eventually develop the sensor systems so that you recognize that there might be a defect at some point of it, and you actually take corrective action autonomously. So we've gone from manual, automated is kind of the next step. You think about G-code and CNC machining, and autonomous is the next step where this process is being sensed and monitored, and you might actually take corrective action in an autonomous way. And we're going towards this. This is kind of closed loop control and simulation are merging up onto that, and eventually we believe it will be completely autonomous. One particular vision of that is a robotic blacksmith, for example. You could imagine that's a system that senses what's going on, makes the shape, makes sure it stays within the process windows that you need for the right metallurgy, and makes the part you need. So that's the vision that we have. That's what hybrid autonomous means in that context.
I love it. And we're all about really all of those processes. And you start to think about the very end of that as you were getting into, putting smart sensors and smart devices on and around the manufacturing process and measuring everything from, whether it's temperature or metal thickness or deformation itself, any of these variables, and then gathering that at scale, right? So it's not just one machine that's doing that. You've got 15,000 machines that are gathering all that information, tying that into, end of use or end of product, end of production quality, finding defects, finding inconsistencies, and then using AI to drive that back into the manufacturing process, and doing that all with just a human being supervising this, as opposed to acting as an operator using our senses to determine whether or not that a product is conforming or not. Not that there aren't still a lot of manufacturers that do it that way, but it really takes that human element out and creates a much more consistent manufacturing process.
You got it completely. And the other thing, kind of conforming. So standards and certification are an important part of that too. So, human blacksmiths are awesome. They can make all kinds of things, but you don't necessarily want to trust them with safety critical parts. They might have a bad day, something goes wrong. But if you have this system that has a sensor there, bunch of sensors there, exactly what happened. You can trace all of that. You can figure out if there's a defect in there, and that eventually we see that as a road to certification and quality. And that's a big part of why we want to have the technical societies involved, because they're the groups that have the organizations to figure out how to certify things and develop the standards. And that's where we want to take this, is to have these systems that can make lot sizes as small as one, and you absolutely know that the quality is there because you've built the sensor suite around it. You know how to interpret that data, and that's why this is a long-term big project. And and we've got the right people involved to do that.
And I think one of the unique aspects of it is you've mentioned the deformation side of things, several times. I remember the first time I saw a deep draw stamping. I just forever, I've just been fascinated by that. You've got I'm telling you what you already know, but for the purpose of our audience, you've got a die that's coming through imagine a piece of stainless steel, sheet steel, and is actually deforming and shaping that particular part around a die, stretching the metal while it's happening. All of the human science that went into that, and I would talk with the engineers worked around metal fabrication for a number of years, and talk with the engineers about it was a combination of an art and a science, and it almost feels like you're taking the art out of that and replacing that with AI and G code and M code.
Well, it's still, yeah, still a lot of room for creativity, and and eventually AI systems can be, sort of creative. You might have, played with some of these things. I think it's something called Dream Studio. You can say, give me a picture of a robot planting flowers in the style of Van Gogh, and it will create these things for you. So robots can start to approximate something that looks like creativity to us. But again, all that, there are rules that we all follow when we do these things. So we know what the limits are on where the metal might break, where it might fracture, where what kind of temperatures we have to hit, and all of these things. So these are things that we want to bake into all of this, and use them more and more as just an augment to human creativity right now. But eventually, just as AI can play Go at levels, play many board games and so forth at levels beyond what a human can see, we think eventually that these AI systems will develop process paths by hybridizing these simple tools, using them on their own, that can develop tools that allow us to make things that we just cannot even imagine right now. Elon Musk, he did a podcast end of last year where he talked about, if you're really good at manufacturing, what you end up doing is putting the right atoms in the right places, and you're not really married to the process. You develop the process to meet the needs of your product, and that's eventually where we want to go. So right now, the state of the art is doing design for manufacturing. We want to flip that and actually develop the manufacturing for design. Develop these processes so that you get exactly what you want. And now, eventually, these are, high value, low volume kinds of products. But if the systems develop nicely, they can work lights out, they can work 24/7, so they can actually be pretty efficient as well. And I think powder bed additive manufacturing shows you that you can have products that don't necessarily produce the kind of tons per hour that a steel mill might, but at the same time that process can produce something that's very high value for you, and that's where we eventually want to go. And the beauty of deformation also is it can scale to fairly large sizes very quickly. You just need larger presses, larger hammers, and you can imagine making things that are quite large and have awesome properties and are very complex. And that's where we hope to take it all.
I think one of the things that folks don't necessarily have an appreciation for is, just how much data we now have, and it's incredible. First of all, I read a statistic not too long ago that I think the average manufacturing company uses about 12% of the data that it has available to it. I think that might even be optimistic, but even if that's true, 88% of their data is going to waste. Another statistic I've heard thrown around is that we'll create more data in the next 3 years than we did in the last 30 years combined, and we really are getting to the point where there's so much data that without the help of artificial intelligence and machine learning, it's impossible to put it to work. But with that help, to your point, I think you're right. I think we will get to the point where AI can design manufacturing processes, and are already getting there in some cases. And I think about my years in manufacturing, and yeah, we talked ad infinitum about design for manufacturability. People on the shop floor would complain if the engineers had any idea how to make this thing, then we wouldn't have had this design in the first place. In your whole, and you've heard it too, in your whole idea of how we're going to flip that model and really say, all right, this is the functional result that we want from this part. Now let's back into using AI and ML to design the process. Am I getting that right?
Yeah, that's right. And don't be constrained by the tool. Don't say, I've just got this 5-axis CNC. This is the way I'm going to make it. I've just got this powder bed thing. Imagine you can mash all of these things up. You can deform to take care of residual stresses. You can deform to take care of microstructure. You can deform. You can imagine putting a weldment on and then deforming that weldment. There's all kinds of ways you can start to imagine mashing these processes up. to do things that you can't do today. And this is what a skilled artisan would do. You put a skilled artisan in a shop with just a simple set of tools, blacksmithing tools, welding tools, oxyacetylene torches, files, and so forth. A skilled artisan can make all kinds of things, and that's really what we imagine that these autonomous systems will be able to do. They've got a toolkit of things that can be controlled digitally, standard sorts of interconnects and dimensional sensing, and just let it go. So it's really kind of the digital version of the artisan's workshop is what we imagine the systems will look like. And once you have those, there's lots of places you can imagine those being used, and that includes making implants near an operating theater. You can imagine using this near forward operating bases where you've got airplane parts or tank parts you need in a hurry. Lots of possible applications. Space stations moon, as well. Mars, absolutely. Right? So small lightweight parts. Yeah, you're never going to put. I shouldn't say never, but it's going to be a long time before we put a closed die forging press into orbit. These are big, massive things, right? But if you can imagine how do you do things incrementally and use other kinds of tools, you can imagine lightweight tools making really big things up in space, and that's another application that we absolutely foresee in all of this.
Absolutely. We did learn not too long ago that we can take something roughly the size of that forging press and slam it into an asteroid at 14,000 miles an hour and change the trajectory of the asteroid. Maybe that'll be the application for the forging press.
I think that's even a small. I don't know what that weighed, but yeah, I don't know exactly what the weight is of a 250-ton press is, but it's it's a lot you got to put into space if you want to do that. So we've got to figure out how to do it differently, and that's what we're all about with all of this.
Yeah, some great things buried into that last discussion. We had Laura Kohler on a little over a year ago. Laura is the vice president of Kohler Company, or your name's on the building. And we talked a lot about the convergence of art and manufacturing, and I really enjoyed your reflection on the artisan and how we can take a lot of what an artisan would come up with, a blacksmith. I mean, you see, they truly are artisans, and then finding ways to turn that into basically a manufacturing process and turn that creativity and capture the creativity and so on into a process autonomously.
Yeah, there's not nearly enough, the overlap between the studio arts and manufacturing. It's pretty strong, and I've got some friends that see us, and that's something we want to actually bake into the center a little bit as well, is really think about deconstructing some of the studio arts things. I mean, they're also good artists is doing exactly the same thing. They've got something that they're trying to make happen, an emotion they're trying to evoke, whatever, and it's getting the right sheen on the metal, the right kind of glazes, the right kind of, its shape and properties again. And that's what we're trying to do. It's just they're interested in different shapes and different properties, but it's the same sort of thing. So I think skilled artisans, tool and die makers, all of those are, my heroes in a lot of this sort of things. And I think sometimes in engineering school, we kind of crushed some of the fun out of it by starting doing it all with equations and analyses of these high productivity processes rather than going back to the gee whiz, how did you make that, and can you do that again, and can you scale it? That's what we want to start with, is that creativity. And I don't want the autonomy to kind of take the fun out of it either, but
it makes it more fun.
This is an augment. This is still the human creativity is where we start with all of this.
Absolutely. Harkening back to another Tech Ed podcast guest, Sue Alsperman, who's the former lieutenant governor of the state of Indiana, was on with us a little over a year ago. She's now the president of Ivy Tech, the statewide technical college system and community college system in the state of Indiana. And she's a PhD engineer, so undergrad, master's, PhD. She said exactly the same thing. She was like, we really have to find a way to, rather than just jamming calculus and physics down the throats of engineering students in their first 2 or 3 years, and then let them do the fun stuff the senior year or junior year. So, see who we can weed out, who isn't tough enough to get through the academic rigor, and then let them do the fun stuff. We really have to flip that. Do you see that similarly?
I agree. I couldn't agree more. Yeah, no, I love the idea of starting with hands-on things where you're actually doing things like, possibly working with ceramics, doing heat treatments, testing things destructively with tensile machines and all of that. And that's such an important teaching tool with all of this. One project I've been working with for many years now is the ASM Materials Education Foundation. This is, again, an outgrowth of one of the technical societies, ASM International, and they hold a ASM, I'll call it we in this case, because I've been part of it for a long time, but we at ASM Education Foundation train something like 700 teachers every year prior to COVID at 40 hours of instruction, and teach K-12 teachers to do these hands-on demonstrations where they're learning about glass and learning about heat treatment and all of these sorts of things. And it's what I would kind of call liberal STEM education that can be used for lots of things, but it's the hands-on part, and that will motivate students then to go on and say, boy, I want to actually design to this. And then you have to actually learn how to do programming and calculus and the physics behind it. And I think that's really the right way to do it, is start with sparking some creativity, sparking some curiosity, and then you go back and say, well, I really want to get good at this. And then you absolutely have to get into the math and the software and the modeling and all of that. But I think that's a super effective way of doing things.
I was one of the folks that when we originally took STEM and people started making it STEAM, I'm like, oh, great. Now we have the art people that are just trying to get their hands on the STEM money, but the more I think about it, and the more that, you kind of see how the creativity on the art side can carry over, one of the things that I've been an advocate of in the course of the last year or two is, rather than looking at the STEAM process as a threat to STEM education, what if we could get these young people that are interested in art and interested in creativity and interested in making things and finding a way to vision something that doesn't exist and then create it? How about we get those people into manufacturing and advanced manufacturing and let them put their skills and their passions to work in a way that benefits the manufacturing world? I've really come around on the whole STEAM thing. Sounds like you have too.
Yeah, I have too. Absolutely. You betcha. So and I think it's all a matter of, we often start with in the way we teach engineering, we start with these mass production processes. We think about things like deep drawing and rolling and extrusion and injection molding and all these things that we use to make lots of things. We're with the center really starting from the other side, thinking about how you make things at quality at small lots, and then can you start to automate all of that. That really is the way additive manufacturing in a sense works that way also. It's really doing things locally, incrementally, but then building things out of that, and then asking, how do you then scale that to making more? And that's really much more the way we're taking this hybridization and autonomy together to build this eventually into autonomous systems.
Right. And taking that design process one step upstream, it's really, in a lot of ways, how do we use digital solutions? So it's not even a lot size of 3 and how do I make 3 good parts, but how do I design that process digitally and then come up with the solution before I ever, build the physical manifestation of that process? The same thing, right?
Yeah, and we think the time is right for this. So our acronym, hybrid autonomous manufacturing, moving from evolution to revolution. So we've had evolution in all of these things like design and sensors and CAD CAM and all these supporting technologies, robotics, AI. And the revolution really is when you can start to harness that to make high quality things at small lot sizes. That's the revolution that we see in that. That's the last part of our acronym. And it's more than just good acronym in engineering. We actually do mean that. So that's where I think we hope to develop a real competitive edge for the United States economy with this NSF funding, with all this as well. So if you can make small lots, they may be relatively expensive. And again, powder bed additive manufacturing has this problem, but they're enabling parts. These are parts that might go into other manufacturing systems. And then from that, you can start doing the mass production with that. Because, setting up a production line takes a long time, and there's a lot of supply chain challenges with that as well. And we want to have the local production to make these high value, low quantity items that might enable Intel to make their chip line and Tesla to make their next automotive line and so forth.
Absolutely. So now let's talk about the research side of this, right? I mean, we've jumped a little bit. We've talked about really cool advancements in manufacturing technology, about mashing up all these different technologies, making them autonomous. So now you have, share with our audience the size of the initial grant that you're sharing with these other institutions, and then how do you use that to actually do the work, do the research? How does that feel, and how does that work?
So number one, we've got some of the best people in the country and the world involved with this from the 5 core institutions. And from the research side, we've got 4 basic research thrusts that this works upon. There's design, which underpins this. So you get a really interesting large design space when you start saying, okay, I have all these processes I might possibly use and mash up to make something. I'm not saying I'm going to make this by powder bed. I'm not going to make this necessarily by deep drawing, but combining these things. So co-designing the process and the component is important. Secondly, we're talking about convergent tools. What kind of tools might we make? What physically would a digital blacksmith of the future look like? So we're thinking about convergent tools. Thirdly, there's control and artificial intelligence that fits into all of this. So we have the tools, we have the concept of what we want to do. How does the system learn how to do that? And then once you have this all digitally, it's not like you've got to train another blacksmith to do it. All of those learning algorithms can be transferred directly to another system, even if it's slightly different. And that's one of the things that we hope to bring into this. And then the last research thrust is really about the material state. As we're doing things and deforming the material, heating it up, possibly adding to it, we are changing the material state. And I'm basically a physical metallurgist, and we know that as we deform, heat, and all that, thermomechanical processing is the way that we make the very best materials. So we want to bring that into it too, and track what's going on bit by bit to make sure we got the right properties in the right place, where we have the highest stress. We know we have the best resistance to fracture and fatigue. And so that's what the full research portfolio looks like. And we're putting programs together that will integrate all of those aspects to serve real needs. Making big forgings without necessarily the big equipment associated with it, making systems that can be used in operating rooms, making systems that can be used at forward operating bases, making systems that can take additively manufactured components and then further improve their properties, for example. These are the sorts of things that we're thinking about. And then we're also thinking about systems that can be used in educational environments. How do we take this and train students to think this way and further innovate with these new tool sets?
Absolutely. I know there's been a multi-year effort in your state around getting young people in the high school, even in the middle school years, excited and interested in whether it's manufacturing, computer engineering, artificial intelligence, machine learning, automation, robotics. I mean, all of those spaces. And I know in many ways, Ohio has led in those endeavors. So are you starting to see at the university level students coming from K-12, from high schools in your state, outside of your state, with a greater knowledge of these types of technologies and a greater familiarity with engineering and with manufacturing processes, or do we have a way to go?
Yes, yeah, we do. And I mean, part of it is work of ASM Materials Education Foundation. We've been teaching high school teachers material science, and a lot of them in Ohio have actually gone off and started their entire courses in material science at the high school level. And a lot of that has to do with processes like casting and glazes and sintering, and how we make glass and polymers and all of that. So we have had a number of students who have seen this in the high school level and have joined our department for that reason. And we want to lean into that even harder with this new grant. All of the NSF engineering centers are very different than typical NSF work. Most NSF projects are really focused on research with a capital R. Is it innovative? Does it have strong intellectual merit? Is it different than what's gone on in the past? We have a broader scope. Really what these engineering research centers are about is using research and technology to improve the human condition, particularly in the United States. So there's four basic pillars that this is based on. One of them is research. Another is engineering workforce development. Third is a culture of diversity and inclusion. And then lastly is an innovation ecosystem to really bring this out into companies. And I couldn't be happier to have an award of this type, because it's not just the research, but it's take the research and try to do good things about it, unambiguously good things. So, and big part of that goes into training the next generation, making sure that we are bringing all types of students in, and we need more people, and we need a more diverse group in this. Again, we have this big trade deficit. I think it has to be eventually fairly close to even if we're going to be sustainable. And that's going to take a big investment in people, technology, equipment. It's going to take a while to get there. It took us a while to get to where we're at today. This is a trend that started back, in the late 70s, early 80s to some of these outsourcing bits. And I think we have to turn that around. and we're happy to be part of the solution is what we want.
And what I love about what I'm hearing you say is, you're doing this research, you're trying to, affect a real problem, which is the trade deficit that there's been an issue in this country, as you suggest, for decades. But you're doing it in a way that's really, really hands-on. It's not a bunch of, it's not a think tank and a bunch of people that are really smart sitting in a lab, just doing work for the purposes of writing a white paper when you're done. You're actually spreading this across. You're working with industrial partners. You're bringing. I just was listening to the different technologies. I mean, you think about manufacturing engineering, controls engineering, materials engineering, computer science. I mean, all of those are going to have to be functions, disciplines that are involved in the research you're doing. So how do you tie all that together? First, on the education side, right? So, I mean, I spend enough time in higher education to know that those are disciplines that don't always play as nice together as we'd like to see them. Sometimes they do. And then the follow-on question is going to be, all right, now that we have the researchers and the kind of pragmatic researchers doing the real work, how do we pull in the industrial employers to make sure that work has valuable in industry?
Yeah. Good question. So I mean, there are kind of some unfortunate rifts. I think, we in kind of higher education haven't paid enough respect to the community colleges and so forth. It's a huge part of our skilled workforce. And we absolutely need, those graduates to carry out all these things that we might dream up here. And we've got to bring that together. With this program, I've been fortunate to be able to kind of pick the team, and I've got great people. I'll point out, Tony Schmitz, he's at University of Tennessee, Knoxville, and he leads something called the Southeastern Advanced Machine Tool Network. And he's putting out basically free courses that can be taken online. And sometimes they've got in-person bits on things like additive manufacturing, CNC, metrology, machine learning, and the like. And he's one of the people, it's an awesome research, but he's also actively reaching out to all kinds of both practicing engineers and technicians, and also reaching out to the community colleges. And we hope to be a resource that they can use to help train some of the next generation of community college instructors. That's an area that I think we're a little bit thin. We need more help getting more people into those kinds of jobs.
Sure. By the way, Tony himself, an alumni of the Tech Ed podcast. We call it the Tech Ed Podcast Alumni Circle. So America's Cutting Edge, I think, if that rings a bell.
So yeah, right. Right. So he's one of the people on our team. And these are the programs that we're going to lean into. The this ASM Materials Education Foundation is another one that we'll use. Here at Ohio State, we have a minority leaders program that really is about the civilian corps for the defense labs. My colleague Mike Graber leads that program. So we want to tie these things together, and this is what we're again, we have a born on date of September 1st, so we're early days here, but I've got a group of people that's very serious about this. We understand the problems and want to be part of the solution. And have me back in a couple of years, and hold us. Hopefully, we have a lot to show.
And we'll most certainly have you back. A couple last questions for you here, Glenn, as we kind of wrap up our time. I kind of feel like we could go on for another couple hours. You mentioned one of the 4 pillars as diversity and inclusion. I'm paraphrasing a little bit, but I know that's a really important part of what you're doing. What is your strategy for reaching out to diverse populations and including them in the work?
Yeah, I mean, first of all, it is just welcoming everybody. So anybody that wants to be involved, we want to be as inclusive as we can to that. We are using at the graduate level, we're using things like forgot what the acronym means with the GEM network, but basically it's a group of college students that identify themselves as being interested in graduate studies that come from underrepresented groups, puts them on our radar. We're leaning into that to bring a diverse set of graduate students into this. And then also we want to reach to groups that typically haven't been part of the conversation with the research universities, the community colleges and so forth. So that's part of it. And they come from rural and urban and all kinds of different environments, and we want to be part of that solution. So again, those are among the plans. And again, we have this Mike Graber's leading this minority leaders group that's really trying to give research experiences to diverse populations to help bring them into leadership positions in the civilian defense labs. Things like Air Force Research Lab are the kinds of groups we want to bring in.
Absolutely, for sure. And no matter where your talent is coming from, almost all those people at one point or another were a high school sophomore, a 15 or 16-year-old. And we like to wrap up every episode of our podcast by asking our guests, and we always get some really sage advice for these young people that listen to the podcast. If you were, Glenn, to give one piece of advice to a high school sophomore as they plan the rest of their life, what would that piece of advice be?
Make something or build something. I know back when I was junior high and high school, things like mini bikes and so forth. And I remember changing gear ratios and making my own gears. And, you learn so much just by cutting your own metal, trying to make things, trying to figure out how to make something better. And there's all kinds of projects, be it studio arts or working on cars. And it's harder and harder for young kids these days to do that than back in my generation. I had an old van that I had to keep running, and painted the thing, did the Bondo work, all that kind of stuff. Those kind of hands-on skills, and then having to live with the results is so important, I think, and something that we end up it's harder and harder to keep that going these days. But that's, I think, my biggest advice. And if you go into a STEM career, having that behind you does enrich all of the mechanics that you might end up learning. It's understand how stress on something, forces turn into stress, and making sure you stay below yield stresses and fatigue limits or corrosion. All these things, making something and trying to live with it teaches you to be an engineer and motivates you to actually learn the deep science behind it. So that would be my big advice. Build something for yourself that and keep at it. And even if it's not great, you learn so much in that process.
And all that building really gives such a context to students as they're advancing maybe to an engineering pathway for what they're learning when they get to their 4-year engineering degree. I can think back to, my years of, in my case, it was pedal bikes. So I used to love to take apart bikes, put them back together, to your point, gear ratios, different handlebars, understanding how to pack bearings. I mean, all of these things, understanding how a derailleur worked on the back of a bike.
Yep.
Really into that. Had to explain a couple blown circuit breakers to my parents when I tried to wire some goofy thing up and plug it into the wall, and it didn't quite end the way that I was supposed to. Not recommending that, because that can end a lot worse than it did for me. But all of those learning experiences from doing things with your hands and actually creating things, so very valuable. It's actually unique advice, and we appreciate you sharing that, as well as sharing all the great things that you're doing at the Hammer Engineering Research Center. Its director, Glenn Daehn, is with us today on the Tech Ed Podcast. We've had just a wonderful conversation. Looking forward to having you back. As you suggest, you're born on date just September 1st of this year. So just a fledgling organization getting going with a lot of support. And we're looking forward to seeing where you go with it.
Thanks. And I'll just add, so if anybody's interested, our web address on this is hammer.osu.edu. That will be updated. There'll be more and more links and so forth as that goes forward. If anybody would like to join our mailing list, hammer@osu.edu. We'll put you on the list and keep you informed as to what we're doing.
And good things you will do. We will put all that information in the show notes as well for our listeners. So tune in there for any of the websites, any of the resources that Glenn Daehn referenced during a discussion. Glenn Daehn, our guest today on the Tech Ed Podcast. Thanks for being with us.
Thank you so much.
Thanks for joining us for this episode of the Tech Ed Podcast. If you haven't already, subscribe, leave a review, and if you like this episode, share it with a friend. New episodes launch every Tuesday, so listen in next week.